So welcome back, guys. Today we continue with the presentation of the first glimpse of the simplex algorithm using firstly the algebraic formulation for the simplex, and then we'll proceed with the dictionary formulation. So remember last time we split A in two parts, the B part, which represents the B matrix of the B columns, the basic columns of the basic variables, and the non-basic columns of the non-basic variables. Similarly, we split X into XP and XN, and CT, the coefficients and the objective, in two parts, the CBT and the CNT, the basic variable coefficients and the non-basic variable coefficients. So the LP, the linear program, now writes as you willing to maximize CTX becomes CBT XP plus CNT XN. And under the condition that AX equals small b, so it becomes capital BXP plus NXN. And since we are relying on the condition that this B is well defined, such that it is a square matrix and invertible, then one can work with this in order to write, if you multiply both sides by B inverse, what you're gonna get is the following. B minus 1 XN on this side. And on the other side, you have B minus 1 B. So basically, you have a kind of a value for XP already, which means you have the expression of, or the values of the basic variables, which is going to be B minus 1B minus B minus 1 and XN. Now, listen to me. Even though we said that...
Doctor?
Yes, sir.
There is one student need to be accepted.
Yeah, he just came in. Thanks. Hello, sir. So I think he left and came back. It's okay. So even though we said that XN represents non-basic variables, in fact, this is quite important to us because we are willing to understand, we will get a very useful information out of this part. Now you can get also the value of the objective at any given point in that case. And in that case, you're going to have your objective, which is equal to CTX, could now be written as CBTXB, which becomes CBT times B minus 1B, which is a constant part if you think of it. Okay, CBTXB, so we multiply CBT by B minus 1B minus B minus 1 and XN. And plus, I'm going to have, with respect to XN, I'm going to have CNT minus CBT B minus 1 and all multiplying XN. And these also would be very useful information to us, okay? We're gonna give them names, okay? And the following, we're gonna give them names, okay? So that's just to summarize what the last part we did last time, okay? Which is a glimpse of the algebraic formulation behind the simplex algorithm. So today we continue, hopefully, with the intention to now to present the, let's say, the most natural way to solve such a linear program, which is the dictionary method, okay? Which is it is just based on the usual or the most natural way to solve a linear system we've seen since high school, okay? So if you remember last time, guys, we solved a tiny little linear program where we found the solution. Let me just get it back before writing it. Yeah, so if you remember, we solved this linear program where we had these two types of products. And at the end, it was written like this. Once we got the formulation, we wrote it as you maximize 6x1 plus 5x2. Okay. And with the standard form, without the standard form first, we wrote it as 3x1 plus 5x2. That's equal to 11. And at the same time, we have 4x1 plus 2x2 less or equal to 10. With the condition that x1 and x2 are both positive, which we call regularly the non-negativity conditions. So that was the problem we saw with graphically last time. Okay, so now let me first write it in standard form before moving to the solution. So in standard form, if you recall, guys, the intention is to write all the condition with which sign, guys? How I'm gonna write these signs, guys, with the standard form? Let me check one of the guys. Yalla, Ahmed. You recall the standard form? Ahmed Bakra.
Yes, doctor.
Yes. What is the intention of the standard form? What is the purpose of it?
It is just to write it as a matrix.
No. Okay, Ali. Ali Al-Ali.
Yes, doctor.
What do you recall from the standard form?
I thought, like Ahmed, it should be in a matrix form.
No. Ammar Shirka.
It's minus E equal
Minus
to
or
11.
Minus or plus here?
Or plus
here.
That's right.
Yeah, because here we have to add a slack variable in order to get an equality. Okay. Thanks, Amma. So same thing we do with the second condition. We add another slack variable. So this way we have no longer a problem with just two variables. We have a problem with two additional variables we call the slack variables, E1 and E2. And they are useful in the solution method. And of course, since you add them to the conditions, you have to add them to the objective with 0 coefficient. So they have no impact on my optimization, in fact. Okay. So this is the standard form, and I'm going to use the standard form to do what? To work on the solution. So first thing, when you are defining when you proposing an algorithm, or let's say, what is an algorithm? An automatic way to solve a problem or to get a solution to a problem, in fact. So let's start with the initialization. So sometimes with some problems, the most maybe what is taken a lot of time, what takes a lot of time at the beginning is to get a hand on a feasible solution. What is a feasible solution? Just some acceptable solution. You're not talking about the best one. So it could be very far from meeting your expectations, but at least you could say, well, I can work with that as a beginning, okay? Here, at this moment, since we have no idea on the form of the feasible region, well, we can still say that one possible feasible solution is to set all the decision variables x's to 0, and just consider that only the slack variables are non-zeros. So if you can say that, in fact, only the non-basic variables, and for non-basic here. So usually we do talk about non-basic variables when the variables are at zeros, okay? So I'm saying x1 and x2 are non-basic here. X1 and x2, which means to me that they are zeros. Just as initialization, okay? So the basic variables are just E1 and E2. And this has some meaning, okay? Because in your conditions here, you could say that, well, I can write the basic variables using the non-basic variables. So if I'm isolating E1, guys, how much is E1 now by itself? It's 11 minus, I can bring all to the other side. So it's going to be equal to 11 minus 3x1 minus 5x2. Am I right? Okay. And at the same time, so what does this mean? It means that, well, it means that E1 is equal to 11 right now. Since you decided to keep x1 and x2 to 0, it means that your slack variable, well, it's just 11. And at the same time, E2 is equal to how much? It's equals 10 minus 4x1 minus 2x2. Well, at the beginning, it means that this is an acceptable solution. This is a feasible solution. It satisfies your conditions, basically. But, well, it does not optimize your objective. For example, if it is a production management problem, well, you're not producing anything. So your profit is 0, but still you have a feasible solution. You're not doing anything here. Okay. Now let's have a look what happens to your objective. So I'd like to keep an eye on my objective here. So my objective, which is to maximize CTX, and I'm calling it as usual. I'm calling it Z. So how much is that now? If you substitute, if you plug E1 and E2, of course, you're going to have 6x1 plus 5x2 plus 0 E1 plus 0 E2, which means, well, this has no importance, so it's going to be still equal to 6x1 plus 5x2. Got it? Okay. So this is an initial solution, or usually here, this is what we call the dictionary method. Let me write it in green. Dictionary. Of course, you understand what is the meaning of dictionary, and at the end of this, you understand what we mean by dictionaries here. Okay. So let's say this is dictionary number 1. Deco for dictionary. This is dictionary 1, okay, or 0 if you wish. Okay, so now I have to ask you a question, guys. So be very attentive, guys. So if someone knocks on your door and says, but we have to increase one of the axes, which one would you pick? Which one you would increase?
X1.
Why?
Because the coefficient is higher than
Yeah,
X2.
because the immediate, expectation is that the immediate profit increases by 1, right? By
Yes.
how much? By 6 for each unit, right? While for X2, it increases only by 5. Okay, you agree? Who said that? Who proposed this answer?
Hassan.
Okay, Hassan, wonderful. Hassan Al-Atiyah, right?
Yes, Doctor.
Okay, now do you guys agree with Hassan?
Yes, Doctor.
Yes.
It makes sense.
So no one wants to ponder his answer. So what if increasing the value of X1 only by 1 unit is not possible? How can I know this?
Can you repeat the question, Doctor?
What could be the outcome if I'm not able to put this 1 unit in X1, considering my conditions? This could happen, right?
Yes.
Depending on what? Depending on the conditions.
Can you repeat it, Doctor? I get lost.
Yeah, so now the question, what I would like to point to Hassan and all the classmates, I would like to point to the fact that if you're willing to increase the value of a variable, you have to first of all think of what is the maximum amount I can put in that variable, right?
Yeah. Yes, Doctor.
Okay. You got my point? And this depends heavily on what? On the conditions you have. And remember, in the previous page, I said, like, there is an information that is quite important. This one I'm pointing to. This gives an idea on the amount by which you could increase the values of the non-basic variables. It depends on the coefficients on the ratio between b-1b and b-1n, in fact. So look at this. So I'm using a different color here. I'm using, this is purple, I guess. So let's point to the column of x1 here in the conditions. Are you with me?
Yes.
What is the maximum value x1 can take? But keeping e1 as larger or equal to 0. What is the maximum value it could take?
11/3.
Yeah. Do you guys agree with Hassan again, right?
Yes.
Yes. Do you agree with Hassan? Yes. 11/3. So out of here, so x1 should be less than 11/3. Yes. What about the second condition? If I look to the line of E2, what is the maximum value x1 can take?
5/2.
So it's 10/4, yes. So now between these two values, 11/3 and 5/2, of course, you guys understand why.
Doctor, I think 4, not 2. Right?
Yes, 10/4 or 5/2.
4 or 2, Doctor. We increasing x1 or x2?
We're increasing x1.
So it should be 5/4, right? The maximum.
No, it's 10/4 or 5/2. Hold on a second. What I'm doing here is dividing the value here of E1 by the coefficients of x1 in this and its corresponding line. The same is 10 divided by 4, right? So it's 5/2. 10/4 is also 5/2, right? Okay. Now, guys, please let me know which one. So which one would you pick? The 11/3 or the 10/4? I think 11/3 is. Why? Yeah, Ahmed. Why you cannot take the maximum? Why you cannot break any one of these conditions?
I'm thinking actually, Doctor. I'm just a little bit confused there.
Yeah, but you're right. You have to pick the minimum, because when you pick the minimum between these two values, 11/3 and 5/2, for sure you're satisfying both conditions.
Yes, that's true.
Yeah, so once, in fact, you are making a move and trying to keep your move, your next step within the feasible region, not get out of the feasible region, because it's very problematic if your move gets you very far from your feasible region. It's very hard to come back. Okay, so you started from a point which is in the feasible region. If you draw the x1 and the x2 axis, the initial point corresponds to the origin, right? So you're seeking, and if you look at it, guys, if you remember how the feasible region looked like, let me go back to it from last time. Yeah, it looks pretty much like this. Okay, so basically you are here at the beginning. This is stage 0. And you decided to move towards increasing the value of x1, right? But you don't know how long or what is the further step you can take, keeping yourself within your feasible region, right? So graphically, this is what you are doing. Now, these bounds come from the conditions. So when I think Ahmed, were you the one who said 11 the minimum?
I think 10/4 is the minimum.
Was Hamid, the Doctor?
Hamid, yes, Hamid. Yes, Hamid. So what is the minimum? This one is 2.5, while the 11/3, I think, is 2.67, right?
3.77.
3 point something. I think.
3.77, yes, you're right. So the minimum is 2.5 for sure, okay? So if you increase in x1, the maximum value x1 can take is 5/2. You guys agree with this?
Yes.
So you see, already we're having a kind of an algebraic way to solve our problem. And this could be wonderfully extended to larger problem with more variables, just because we are basically just working on solving a linear system, but trying to making smart moves, okay? So, but I added this graphic so you can understand here in 2D what's going on. You're moving from the origin, which is the initial solution, to an X point. Now, don't expect that the first move you can make, you're going to have, or you can take, is going to lead you immediately to the optimal solution. This is not going to happen in general. So let's work out the second dictionary and see with this move what should be written, okay? So with the second dictionary, guys, what's going to happen? There is a small manipulation we can do. So what am I going to do? I'm going to take the line that gave us the best bound for x1, which is the line of E2, right? I'm going to work with it so that everything is written in normal form. So usually it used to be written like this. It's 10 minus 4x1. I think minus 2x2, yes. So once you decided that x1 should enter the basis, it means immediately that E2 should leave, right? Because if you're pulling x1 to its, or stretching it to the max, it means E2 is going to be equal to 0. So E2 should be to the left side, to the right side now. So it's basically writing it again as 4x1 equals 10.
Now we choose x2 instead of x1, Doctor.
No, hold on a second. I didn't finish. You see, now I'm just rewriting it in a way that is acceptable for my dictionaries. And now I'm dividing by 4, okay? I have to keep track of these lines. It's very important. So I divided by 4, guys, still following me?
Yes.
Yes.
Okay.
Yes, Doctor.
And now the 10 over 4, of course, you can simplify it. And finally, you have your first complete line. 5 over 2 minus 1/2, I think, of x2 minus 1 over 4x e2. So that was, in fact, the second line, but rewritten once x1 entered, okay? Now, don't forget you had another condition which said that E1 equals 11 minus 3x1 minus 5x2. Well, this is what that was line 2, huh? Or row 2, if you wish, if you were just solving a linear system of equations. So this is line 1. I'm rewriting it because usually, initially it was written as, I think, 11 minus 3x1 minus 5x2. Now, what is bothering me now here, since x1 is now a basic variable, what is bothering is that x1 appeared on this side, okay? I mean, this has to be substituted with this new expression. So E1 is equal to 11 minus 3, I open a big bracket, 5 over 2 minus half of x2 minus 1 over 4 E2. There is some purpose for doing that. The purpose is to keep the same spirit, the same idea behind the fact that you are keeping the basic variables on the left and the non-basic variables on the right. You got it? Okay, so there is no way to keep x1 on the right if it is a basic variable now. Only non-basic variables. So let's do some math here. 11
minus 5x2, you forget it.
Minus 5x2, you're right. Thanks. So now I have 11 minus 15 over 2, am I right?
Yes.
Which is 22 minus 15 is 7 over 2, am I right? Okay. Now for the x2s, I have minus 5 and I have a plus 3 over 2. So it's going to be minus 7 over 2 also. You can do the math at the same time with me, guys, if you wish. Okay, sometimes I go quite fast, but with a lot of risk, a lot of mistakes. And the minus 3 multiplying the 1 over 4, the minus 1 over 4 gives plus 1 over 4.
Doctor,
Yes, sir.
Ahmed said he is disconnected.
Yes, I didn't him again. So what's going on, Ahmed, with you? Are you on the road? Okay, so let's check now. Sometimes, guys, 10 seconds to check again our computation. Let's see how did we find the 7/2. We had 11 minus 15/2, right? Which is 22 minus 15, 7/2.
Doctor,
Yes, sir.
I'm sorry, but I lost connection and I didn't follow up. Can you just repeat, please, quickly?
From where did you lose connection? My pleasure, yeah. From where?
From the previous slide.
Oh, so what did we do, guys? We went back here.
Yes, from picking the minimum.
Yeah, from picking the minimum. We said we picked the minimum because we want to be within the feasible region. We pick a value of x1 that satisfies both conditions here, okay? And the one that satisfies both conditions is to set x1 to 10/4, okay? Since we made this move, I had to rewrite the line 2 from where I picked the 10/4, okay? So to write it again, I moved to another table where we took the line 2, which is here, as E2 equals 10 minus 4x1, and I brought 4x1 to the left side and E2 to the right side, first of all. Then I divided by 4. So I get x1 equals 10/4 minus half of x2 minus 1/4 E2. And which means I got now a new line 2. Okay? Which is consistent with the fact that when we wrote these algebraically, we said that xb should be equal to b minus 1b minus what else? We said b minus 1 and xn. So that's why the basic variables should be on the left and the non-basic variables on the right. So x1 is a basic variable, now it is on the left, and the non-basic variables, which are x2 and e2, are on the right. Got it? Now, since I have an expression, a new expression for x1, I took line 1 and I substituted x1 with this new expression. So that's why I opened this bracket instead of writing x1. It is 5/2 minus half of x2 minus 1/4 e2. And I did the math now. I did 11 minus 3 times 5/2. So it's 11, which is 22 minus 15/2, 7/2. Then I had minus 3 times minus half, which is plus 3/2, minus the 5, which is minus 10/2. So I get minus 7/2, okay, for x2. And finally, the coefficient in front of E2 is minus 3 times minus 1/4, which is 3/4. Got it?
Yes, doctor, thank you.
Okay, you're welcome. So now, this is a new dictionary, in fact. Your new dictionary is this one. You have these two lines on which I'm pointing with stars, okay? I marked with stars. Now, the last part in my dictionary is the objective, because once you did a move, for sure there is an impact on the objective. So I'll take again my objective, which was equal to 6x1 plus 5x2. So Z, so let me go back to my green. So Z, which was equal to 6x1 plus 5x2. Now it's no longer 0, right? I have to multiply 6 by the value of x1. How much is x1? It's 5/2 minus half of x, 5/2 minus half of x2 minus 1/4 e2. And immediately, guys, you could notice that the z has moved out from 0. It's no longer 0. So how much is that? Z is 30/2, okay? Right? Are you with me, guys?
Yes.
30/2. And how many x1s now I have?
No x1, only x2.
Sorry?
No x1.
Only x2s. How many x2s?
Minus 3 plus 5.
Minus 3 plus 5.
Plus 5.
Minus
Which is,
3 plus 5.
plus 2.
How much is that?
Plus 2.
Plus 2x2. Okay. And what else?
Minus 3 over 2 E2.
3 over 2 or minus 6 over 4. Okay. Now I have a question to ask. First of all, do you all agree with this result? I have 6 times 5, 30 over 2, which is 15. I have minus 6 over 2, which is minus 3 plus 5. So I get how much? 2x2. And then I have minus 3 over 2 E2. Okay. Now there is an indication. Something here is telling you, it's whispering the fact that you've reached the optimal or no. The optimal or no. Did you reach the optimum, guys? Is this solution optimal? So in other words, is this the best you can have for Z?
I think yes, because we maximize x1.
No, you did not maximize, brother. You did not maximize yet because there is something here that is pointing towards the fact that you still can increase the value of Z. The fact that you have a positive coefficient in front of x2, right? So if x2 can take a positive value, Z could be improved. Okay? So that's why we said previously from slide 1, we said that it's very important that you keep an eye on these coefficients, the ones that appear in front of the non-basic variables in the expression of the objective. You got it? So now hopefully we understand why these coefficients in front of the non-basic variables in the objective are important, because they will be telling us whether the solution we have in hands is optimal or not. And the coefficients in the conditions will tell us what are the bounds on the new entering variables, if you wish. Okay, so let me go back to it. So now you see this 2, in fact, is indicating that if you're willing to improve the value of Z or increase it, well, you can improve by increasing the value of x2. You see? Okay, why? So the answer to optimal or no, because the coefficient of x2 can be larger than 0. So the value of x2 can be larger than 0 because of the 2 here. Okay. So I have a question now. Now x2 is entering. So that's our decision, right? Do you agree with this, guys? So x2 enters the basis. So question to you, if you are willing to improve or increase the value of x2, what is the new max value for x2? The same as we did, similar to what we did in the first iteration. So I should look to what? Onto my conditions, right? My lines. So what does these conditions suggest? What is the maximum bound for x2 from the first line? The first line is here, the one that is below. So
maybe 1.
Yes, x2 cannot exceed 1, right? Because you have 7 over 2 and over 7 over 2. What about the second one? x2 cannot exceed
5.
It cannot exceed 5. Okay, so basically it means that now the x2, if it enters, well, you're gonna be having to remove e1 from the basis. So you see, you understand why now e1 was in the basis. Now it gets out of the basis and it gives its place or position to x2. So e1 leaves. Okay. In the first iteration, in fact, what we did, which variable entered, guys? x1 enters. Yeah.
Yes.
x1 entered the basis. And which variable left the basis? e2 left, right? Okay. Leaves. e2 leaves. I'll write it upstairs a little bit so I won't be messing with my eyes. Okay. So, and every time you have to update or keep an eye on the way the basis is updated. So if you want to go back to it, in the second deco, the basis consisted of which variables, guys, here? The variables in the basis are E1 and X1. Am I right? Yeah, E1 and X1. Of course, the non-basic is the complementary. And then the next one, the new basis is going to be updated. So I'll move to a last now iteration. And this is going to lead to the optimal solution because we know that, we know about the outcome, we know already about the solution, right? So, but the move I'm going to make is to make X2 enter the basis. So X2 enter the basis, which means I'm taking this line with me, okay? So this is going to be the dictionary number 3 and the last one here. So if we take in this line, which is E1 equals 7 over 2 minus 7 over 2 X2 plus 3 over 4 E2. X2, right? And plus 3 over 4 E2. Okay, let's work a little bit, guys. So if I bring the X2 to the other side, I'll get 7 over 2 X2 by itself equals 7 over 2 minus E1 plus 3 over 4 E2. Okay. Yeah. So now I'm multiplying by 2 over 7 both sides, huh? Yeah. So I'm going to get X2 equals 1 minus 2 over 7 E1. And if you multiply both sides by 2 over 7, guys, how much you get? You get 6 over 28 or 3 over 14. Huh? Okay, so this is a new line 1, in fact. This is the new line 1. You had to keep an eye on it. Huh? So this is the new line 1 you obtain. Correct me if you see any mistake, please, guys. You have having more sets of eyes is much.
Correct, Doctor.
It's correct. Now, of course, now since I have a new expression for X2, I'm going to plug it in the second condition I had before. So I have X1, which was equal to how much? 5 over 2. And I think it was minus half X2. So here I stop, I'll open brackets and I plug in X2. Hopefully you follow the same idea. So this takes the place of X2. That part is what? This is X2 in fact. And I think we had minus 1 over 4 E2. Okay, so all I gotta do now is just to compute the numbers. So it gives me X1 equals how much, guys? 5 over 2 minus half, it's 2. Got it? Now, how many A1s I'm gonna have? I'm gonna have minus half times minus 2 over 7. So it's gonna be plus 1 over 7 E1. And if I collect the coefficients of E2, I have minus 3 over 28 minus 7 over 28. So it's minus 10 over 28 or minus 5 over 14. E2. You can check also. I can do it again. It's minus 3 over 28 minus 1 over 4. So it's minus 3 over 28 minus 7 over 4 is minus 10 over 28, which is minus 5 over 4. So basically, I'm done with the two conditions. All I have to check now whether the objective still can be improved or not, and conclude on the optimality of my objective. So let me go back to my objective. It was equal to 30 over 2 plus 2x2. So I'll open a bracket for x2. And you see these two additional units that add up to the value of my z, which means that I can improve it. So this takes the place of x2, of course. You understood this before. And don't forget, I still have -3/2 e2. Okay. So now what is the new value for z, guys? It is equal to 15 plus 2. How much is that? 17. Now, how many E1s do I have? I have -4/7 E1. And what about the E2s? I'll have plus 6/14 E2 minus 3/2. Right? 6/14 is, so let me write it here.
21/14 and 3/14, it's
6/14
15/14.
minus 3/2 E2, okay? So this number, guys, is 6 minus 15, huh? 6 minus, multiplied by 7, 6 minus 21.
15
So
over
minus-
14, I think.
Yeah, minus 15/14. Okay, so now the computation is fully in fractions, as you see. So, question to you now. You've reached this solution. You can write it like this, forget about this, okay? All these coefficients you see now in the objective are negative or no? The coefficient in front of E1 is negative, and the one in front of E2 is also negative, right? What does that mean? It means this is the optimal solution. You cannot improve it anymore. And recall that the z equals 17 is exactly what we found graphically last time. Okay, so this z is optimal. Okay.
But doctor,
Yes, sir.
how can, what is the value of x1 and x2?
Here they are. This is the 1 and this is the 2. Remember last time we said that at the optimum here, x1 should be equal to 2 and x2 equals to 1. Okay?
Yeah.
And this is what happened here, in fact. Look, in fact, these two moves, graphically, this is what we did. The first iteration brought us to this point, right? Where only x1 was positive and x2 is still 0. And the second iteration brought us to this point, which was the optimal one we found last time. Okay? So this is done with two only variables, but it could be easily extended with more than two variables and two conditions. And there is an advantage to see this. It is telling us at every moment what is happening with our conditions. But the main disadvantage is we have to carry this formulation, the names of the variables, instead of using the light, let's say the lightweight of handling matrices and handling tableaus, in fact. Okay, and this is hopefully what we'll be seeing next time, inshallah. So guys, do you have any question on that? Okay, so I'll stop recording here. I'll just quickly